All right, sorry if I sound bitter. I just spent an hour completing this entire video just to have my screencast freeze at the end and lose it. So I guess we're going to do this as take two. So we're going to start chapter 6 with section 6.1, looking at area between curves. So it says the area A of a region bounded by the curves y is equal to f of x and y is equal to g of x, and the lines x is equal to a and x is equal to b, where f and g are continuous, and f of x is greater than or equal to g of x for all x in the closed interval from a to b, is given by the integral expression, where the area A is equal to the integral from a to b of the larger function f of x minus the smaller function g of x, which we are integrating with respect to x. And if you take a look at like what's being computed, when we take the integral from a to b of f of x, that is computing like all of the area there in green. When we subtract the integral from a to b of f of x, that's taking away all of the area in red. And then when you combine those two ideas, that's going to leave you with the area in black, which is the area enclosed between those two curves. All right, so let's get into some examples involving this. So the directions here ask us to find the area of the region bounded above by y is equal to e raised to the x power, bounded below by y is equal to x, and bounded on the sides by x is equal to 0 and x is equal to 1. So I'm going to draw just a quick diagram modeling this. So if we think about the function y is equal to e raised to the x power between the x values of 0 and 1, that's going to contain the point 0, 1, and 1 comma e, which is like 1 comma 2.7. And that's going to be an exponential curve looking like so. And then the line y is equal to x between 0 and 1 contains the point 0, 0 and the point 1, 1. So the area enclosed by those two curves is going to be the area of that shaded region. Okay, so if we want to compute that area is going to be equal to the integral from 0 to 1 of the larger function, e raised to the x power, minus the smaller function x, which we are integrating with respect to x. Okay, so we're going to go ahead and take the antiderivative. So the antiderivative of e to the x power is e to the x power minus the antiderivative of x, which is x squared over 2. And then we're going to evaluate that at our limits of integration, which are 0 and 1. So when we plug in 1, that gives us e to the first power, which is e, minus 1/2. And when we plug in 0, we get e to the 0 power, which is 1, minus 0. So that winds up giving us e minus 3/2 for that area. And again, because the area lies above the x-axis, that area is positive. But something that I want you guys to be aware of is when we calculate area between two curves, no matter whether the area lies above the x-axis or below the x-axis, the area between two curves is always going to be some positive quantity. Okay, as long as you have it set up properly. Okay, so next example says to find the area of the region enclosed by the parabolas y is equal to x squared and y is equal to 2x minus x squared. Okay, so if we draw a graphical representation here, the function y is equal to x squared is going to look like this. So that's a parabola with the vertex at the origin that opens up. The function y is equal to 2x minus x squared. That has x-intercepts at 0 and 2. The vertex is going to be at the point 1, 1, and that graph opens down looking like so. So the area enclosed between those two curves is that area there in black. Okay, so if we want to compute that area, we are integrating from 0 to 1. So the x values that enclose that area start at x is equal to 0 and finish at x is equal to 1. And then we're going to take the larger function, which is the function that bounds the area on top, 2x minus x squared. And then we're going to subtract the smaller function, which is the function that bounds the area from below, which is the function x squared. Now the thing you need to be careful of here is if your function that bounds the area from below has multiple terms, which this one doesn't have, but if it does have multiple terms, you have to make sure you subtract that entire function. Okay, so if we want to compute, we're going to just combine like terms, so we get 2x minus 2x squared, and then we can go ahead and integrate that term by term. So the antiderivative of 2x is x squared, minus the antiderivative of 2x squared is 2/3 x cubed, which we're going to evaluate at 1 and at 0. So when we evaluate at 1, we get 1 minus 2/3. We evaluate at 0, we get 0 minus 0. So that area there is going to be equal to 1/3. Okay, let's move on to the next example. Sorry, I wanted to throw this example in. I forgot to include it in my original lesson. So directions here say to find the area of the region bounded by the function y is equal to x squared minus 2 and the x-axis on the closed interval from 0 to rad 2. Okay, so again, find the area of the region bounded by the function y is equal to x squared minus 2 and the x-axis on the closed interval from 0 to rad 2. Okay, so again, if we draw a graphical representation of this, that's the graph of the function x squared shifted down 2 units. And that is going to have an x-intercept at rad 2. Okay. Now, when this problem says to find the area of the region bounded by that function and the x-axis, that means we're being asked to find the area enclosed by 2 curves. Okay, so the function that bounds the area from above is the line y is equal to 0. So we're going to take the integral from 0 to rad 2 of the function that bounds the area from above, which is 0, minus the function that bounds the area from below, which is the function x squared minus 2. So I have to make sure that I subtract that entire quantity. Okay, so that's asking me to find the area enclosed by those 2 curves, which should be a positive quantity. So let's check and see if it is. So that's going to be the integral from 0 to rad 2 of, when I distribute the negative, we get negative x squared plus 2, which we're integrating with respect to x. And then we can go ahead and take the antiderivative, which is negative 1/3 x cubed plus 2x, which we're going to evaluate at rad 2 and at 0. So when I plug in rad 2, we get rad 2 cubed, which is 2 rad 2, times negative 1/3 is negative 2 rad 2 over 3, plus 2 rad 2 minus, and then when we plug in 0, we get 0 plus 0. So this is going to become negative 2 rad 2 over 3 plus 6 rad 2 over 3, which is equal to 4 rad 2 over 3, which is what we want. We want that quantity to be positive. Now, if the question asked us to just evaluate the integral from 0 to rad 2 of the function x squared minus 2, so when we evaluate the integral only, Because that area lies below the x-axis, that integral should give us a negative area. And if we computed the value of that integral, that should give us negative 4 rad 2 over 3. Okay, so the directions in the problem when it says find the area bounded by that function and the x-axis, that in essence is asking you to find the area between those two curves. Okay, let's move on to the next example. So the next example is going to be a calculator example. So the directions here ask you to find the approximate area of the region bounded by the curves y is equal to x divided by the square root of x squared plus 1, and y is equal to x to the 4th power minus x. Okay, so you're going to need to input those functions into your calculator and then set up and evaluate an integral on your calculator to compute that area. Okay, so graphically you should have wound up with something that looks like this. So the graph of y is equal to x over rad x squared plus 1 looks like so. Y is equal to x to the 4th power minus x looks something like that. So the area enclosed by those two curves is the area of that shaded region. Okay, so the two things that you would need to find are the intersection points. So the first intersection point occurs at the origin, and the second intersection point occurs there. So you'd want to take the intersection point that you stored, which I'm just going to round that decimal right now. So it's 1.181. The lower limit of integration is 0. And then we're going to take the larger function, so the function that bounds the area from above is x over rad x squared plus 1 minus the function that bounds the area from below, which is the function x to the 4th power minus x. And again, you want to make sure you subtract that entire quantity, that entire function. So when you evaluate that on your calculator and round to 3 decimal places, you get that to be approximately 0.785. Okay, so let's move on to the next thing we want to talk about. We want to come up with a more generalized rule for finding area between two curves. Okay, so when we started the lesson, we found area between two curves where one function was always bigger than the other. But that's not always going to be the case for us with functions. We can have functions flip-flop where one function is bigger than another on one interval, and then it changes where the smaller function is now the bigger function on another interval. So we want to come up with a more generalized rule to allow us to compute the area between two curves. So the area between the curves, y is equal to f of x, and y is equal to g of x, and between x is equal to a and x is equal to b, is given by the following integral expression. So the area is going to be equal to the integral from a to b of the absolute value of f of x minus g of x, which we are integrating with respect to x. Okay, so when we have our integral expression set up as the absolute value of f of x minus g of x, there are two possible outcomes for that absolute value function. And the first one is going to be when f of x is greater than or equal to g of x. So if f of x is the larger function, that means that f of x minus g of x is going to be positive. And when we take the absolute value of something that's positive, that's just going to be equal to the expression itself. So the absolute value of f of x minus g of x is just the function f of x minus g of x. It's the bigger function minus the smaller function. The second possibility is when g of x is greater than or equal to f of x. So if g of x is the larger function, when we take the absolute value of f of x minus g of x, the value that we're getting inside the absolute value bars is going to be negative. And when we take the absolute value of something that's negative, we take the opposite of that expression, which is going to be the opposite of f of x minus g of x, which gives us the function g of x minus f of x. So when we have our integral set up in that way, we always take the bigger function minus the smaller function. Okay, so let's get into some examples now illustrating this. So the directions for the first one say to find the area of the region bounded by the curves y is equal to the sine of x, y is equal to the cosine of x is equal to 0, and x is equal to pi over 2. Okay, so let's go ahead and draw, again, a graphical representation of this. So the graph of sine between 0 and pi over 2 is going to look like this. So it contains a point 0, 0, and the point pi over 2 comma 1. So that's the graph of y is equal to sine. The graph of y is equal to cosine. It's going to contain the point 0, 1 and pi over 2 comma 0. Okay, so that's the graph of y is equal to the cosine of x. And then if it asks for the area bounded by both of those curves, the area that we're talking about are these two areas here in black. And the reason it's not the unshaded area, the unshaded area would be the area enclosed by those curves and the x-axis, not enclosed by those two curves. And the line x is equal to 0 and x is equal to pi over 2. Okay, so when we look at this here, there are a couple things that we need to determine. Number one is we need to determine where the intersection point occurs. And the intersection point is going to occur where cosine and sine are equal. And that happens at x is equal to pi over 4. And the second thing we have is that the function that bounds the area from above and the function that bounds the area from below change at some point. So if we want to set up an integral expression to compute the area here, we're going to actually have to set up two integrals to compute that area. Okay, so the first integral is going to be the integral from 0 to pi over 4. And on that interval from 0 to pi over 4, the larger function, the function that bounds the area from above, is cosine, minus the smaller function, which bounds the area from below. That's going to be sine. And then we're integrating that with respect to x, plus. For my second integral, for the second area, we're taking the integral from pi over 4 to pi over 2. The function that bounds that area from above, the larger function there is going to be sine, minus the function that bounds the area from below, the smaller function is cosine. And we're integrating that with respect to x as well. Okay, so we're just going to go through and take the antiderivative. So the antiderivative of cosine is going to be sine, minus the antiderivative of sine, that's negative cosine. So that's going to change that sign to plus. So that's sine of x plus cosine, which we're going to evaluate at pi over 4 and 0, plus antiderivative of sine is negative cosine, minus the antiderivative of cosine, which is sine. And then we're going to evaluate that at pi over 2 and pi over 4. Okay, so we're just going to evaluate the antiderivatives at the limits of integration. So we get the sine of pi over 4 is rad 2 over 2, plus the cosine of pi over 4 is also rad 2 over 2, minus the sine of 0 is 0, plus the cosine of 0 is 1 plus negative the cosine of pi over 2 is going to be 0 minus the sine of pi over 2 is 1 minus, and then negative cosine of pi over 4 is negative rad 2 over 2 minus the sine of pi over 4, that's rad 2 over 2. So when we combine all of these parts, we get rad 2 minus 1 plus rad 2, which is 2 rad 2 minus 2 for the area of those two shaded regions. All right, I'm going to break the video up into two parts so I don't have the same problem as last time where it freezes up.